Welcome. In this session, we'll solve an example of an RLC circuit, how to find the response, or in other words, voltage or current in an RLC circuit. And this exam in this session, we'll solve an example where we remove the source. So in other words, this will be a source-free RLC network, right? So let's take an example. So let's suppose we have a network. This is a very simple example of this RLC network. So let's suppose we have a capacitor here. We have a resistor here, and we have an inductor here. So let's suppose there is a switch which is connected to the position A, and here is the position B. So let's suppose the switch was connected to this, and at t equal to 0, it is moved from position A to position B. In other words, the switch was connected there for a long time. Let's suppose this is 1 volt. Very simple example. So this is 2 ohm. So this is, let's suppose 2. This is 1/2 farad, and this is 1 Henry. Let's suppose we have to determine the current that flows through this inductor. So let's suppose we have to find I of t, right? For t greater than 0. So our goal is to find I of t for t greater or equal to 0. Means when we close the switch, what happens to the current that flows through this inductor? Now, as you can see, the switch is getting closed at t equal to 0. So what was the condition before this switching action? Now, before the switching action, let's suppose at t equal to 0 minus, just before the switching, what was the condition? You can see the switch was connected to position A. In other words, the capacitor was connected to the source. Okay, so what will happen in the capacitor? It will charge. And we will assume that it was there for a long time, means the capacitor is in steady state. So if it is in steady state, that means if this will be fully charged. So in other words, capacitor will be fully charged, means it will now act as an open circuit. So this is the equivalent circuit at t equal to 0 minus. So capacitor will be open circuit. So this is 1 volt, this is 2 ohm, and let's suppose the voltage across the capacitor is Vc of 0 minus. Right, so the switch is connected to the position A, right? So now the rest of the circuit, so the remaining portion of the circuit is here. So this is the 2 ohm, this is 1 Henry, and this is I of 0 minus, right? Now from this network, you can see no current will be flowing here. Why? Because this is an open circuit, so no current will be flowing. That means there will be no drop in 2 ohm resistor. As there will be no drop in 2 ohm resistor, Vc of 0 minus is simply across the voltage source. So this voltage is directly across the voltage. So what is the Vc of 0 minus? This is simply equal to 1 volt. As nothing was connected in this remaining portion of the network, you can see that in other words means this I of 0 minus is simply 0, right? As nothing was connected there, so this is simply 0. Or you can see this is an open circuit, so nothing will be flowing there. No current will be flowing there, right? So this is the equivalent circuit of this. Now, after we move the switch from position A to position B, so after we connected the switch from position A to position B, so for t greater or equal to 0, t greater or equal to 0, what is the equivalent circuit? So the equivalent circuit looks like this. So let me write the value. This is plus minus 1 volt. This is 2 ohm. This is 1 by 2 farad. This is 2 ohm. So this will be I of t. This is 1 Henry. Sorry, this is an inductor. This is not a capacitor. This is an inductor here. So this is 1 Henry. So, but we have VC of 0 minus is equal to 0. So VC of 0 minus is equal to 1 volt. So if VC of 0 minus is 1 volt, what is VC of 0 plus? That's again equal to 1 volt. Why? Because capacitor voltage cannot change suddenly. Also, if I of 0 minus is equal to 0, what is I of 0 plus? That's again equal to 0. Why? The inductor current cannot change suddenly. So the reason is the capacitor voltage cannot change suddenly. Capacitor voltage cannot change suddenly. And the reason for this is the inductor current cannot change suddenly. So this is the reason. So the value of I of 0 plus is 0 and VC of 0 plus is. So we have the initial value of the voltages and currents in inductor and capacitor, right? So we have the initial values. So now what we'll do, we'll use Laplace transform and we'll replace them by their equivalent circuits. And one more thing, there is, as this circuit does not remain in the calculation, right? There is nothing, no current will be flowing from this. So there is no use of this. So what we'll do, we'll write the equivalent model of this in the Laplace transform, right? So what is the equivalent circuit of a capacitor if it has initial value, if it has some initial value? We know the model is, and what is the equivalent model of an inductor if the initial value of the current is 0? Now we have learned this in the previous lecture. If we go back to the previous lecture, you can see if the initial value of the capacitor is not equal to 0, then the equivalent model is this or this. So we'll use this time this one. We'll use this one. So what will replace the capacitor with? 1 by Cs plus V naught of 0 divided by S. What is V naught of 0? 1 volt. Same way, if the initial value of the inductor is 0, so we'll replace simply the inductor by Ls, right? We have studied this in the previous class. So let me draw the equivalent model of this capacitor. This, right? So let me draw the equivalent model of this circuit in the Laplace transform domain. So capacitor we will replace with simply 1 by Cs, and C is 1 by 2 plus a voltage, initial voltage. And initial voltage is 1 volt, so it will be 1 by S, and 1 by Cs will be simply 1 divided by 2 divided by S. Because it is 1 by Cs, 2 will come in the numerator side. Then we have resistor. We know nothing happens to the resistor. And inductor we will replace by simply Ls. So L is 1, so it will be S. And we'll say now the current that is flowing here is I of S. So our goal is to find I of S. So use the KVL of this network. So writing the KVL, so it will be minus 1 by S plus 2 by S times I of S, because this is an impedance. Impedance times current is voltage drop, plus 2 I of S plus, this is the impedance of this branch, and impedance of this branch is simply S. S times I of S is the voltage drop, so that's equal to 0. So this is the KVL. So simplifying this, what we'll get? We'll get 2 by S plus 2 plus S, taking I of S common and transferring this term on the right hand side. So it will be 1 by S. So it will be simply simplifying this 2 plus 2S plus S square divided by S. I of S is equal to 1 by S. Now 1 by s will get cancelled from these two sides. So I of s will be simply 1 divided by s squared plus 2s plus 2. So to determine I of t, we have to take the inverse Laplace transform. So I will bring it in the one special form. So I will write it 1 divided by s plus 1 whole squared plus 1. You can check this will be equal to this, right? S squared plus 2s plus 2 is simply s plus 1 whole squared plus 1. So I will write it like this. So this is I of s. Now, if you remember the shifting theorem, if you remember the shifting theorem of Laplace transform, so we know the Laplace transform of e to the power of at sine of bt is simply b divided by s plus a whole square plus b square. What is b equal to? B is 1. What's a equal to? A is again equal to 1. So the inverse Laplace transform of this quantity is this. So that means inverse Laplace transform of this will be simply. So from this, if we take the inverse Laplace transform, so taking inverse Laplace transform of I of s, so it will be simply I of t is equal to e to the power of minus t because a is equal to 1 and sine of bt, b is equal to 1, so it will be sine of t. So this is the current flowing in the network after we change the position of switch from A to B. So this is the current flowing from, this is the current flowing in the network after we move the position of the switch from 1 to 2. And what we use it? We use the Laplace transform, as I have already mentioned. So for second order circuits, Laplace transform is the easier approach. So this is a second order circuit because this contains both L and C. So this is a second order network. So we'll use Laplace transform to find the current or the response of this network. And it becomes very easy to find the using the Laplace transform approach, right? I hope you get the answer. In the next session, I will solve with the source. So what, as we connected this, one more thing before I leave, as we kind of move the position of the switch from A to B, right here. So if we connect to this, so capacitor is charged. So what will happen to this charge? Or what will happen to this energy that is stored in the capacitor? It will get dissipated by 200. So the current that you'll go that you got should decrease with time. Now, if you plot this expression, indeed, this shows a decreasing behavior. Means the current that flows here, it looks like because of this e raised to power minus t, it is going down. It is sinusoidal, but it is going down. So as time progresses, the current is decreasing. In other words, the charge stored in the capacitor is decreasing, right? So indeed, this is a source-free circuit, right? So this is an example of a source-free circuit. All right. So let me end this session here.